In this class, we'll be talking about a circuit simulator that we will use to understand the properties of electric power. In the winter semester, we've been discussing several methods how we can solve electrical circuits, and we have been using a simulator PartSim, which is web-based. Today we'll be using a more advanced simulator. So we will simulate a very simple circuit, but at the end we'll be able to perform mathematical operations with the results from our simulation so that we can understand the power in an electric circuit. So let's take a look on how to use this simulator and how to draw some basic circuit. In the LT-SPICE simulator, you need to define the components that you will be using. There are some components that are already available. You can see them here on top. We have resistors, capacitors, inductors, and then we have other components such as voltage sources, semiconductors, and so on. So we will simulate a very simple circuit which will have only three components. It will have a resistor, an inductor connected in series, and a power supply which will produce an AC sine wave. So let's take a look on how we can create a circuit. We will go to components, and here we have the libraries that we have currently installed in LT-SPICE. For our simple simulation, we can use the basic components. We don't need to install any additional libraries, but there are many libraries available on the internet which can be used very simply in LT-SPICE as well. So I will build the circuit starting from my power supply. So here it's called voltage. On the symbol we can see that initially it will be a DC voltage supply, but if we read the description we see that it may be also an AC supply, a pulse supply, and so on. So let's put this in our circuit. It will be called V1, and the two other components will be a resistor and an inductor, and they will be both connected in series. So we just drag very simply those components to our circuit. We can zoom in and out the circuit. We can drag with the left mouse our whole circuit. And I will just add my second component, my inductor. And now I can connect the circuit together. So let's do it like this. So this will be my connection between the power supply and the inductor. And then I will connect the inductor to my resistor, and I will close the circuit from the resistor into the power supply. Now we need to add one more component in order to make it work, and this is our ground reference. If you are connecting a real circuit, you can connect it like this, and then you basically take your voltmeter and measure whatever voltages you require, or an oscilloscope to measure the waveform. In simulation you need to always have some reference point that is used as ground, and this ground is then taken as a voltage 0. So here is my reference point, ground, and I will drag it in my circuit, and I will select where should I place it. Now for simulation it doesn't really matter where you put the ground reference point, but in order to keep the same positioning as in a real circuit, I will ground this point, the minus point of my power supply. You can see that now I have placed the component somewhere in my circuit, but I need to move it here to this position. This can be easily done by changing the mode and by dragging the component that I want. So I will place it over there, and now I just need to finish the wiring between the ground and between my circuit. The next step is that we need to define the parameters of our circuit. So I will start with the voltage supply. We will right click on the symbol, and initially it is giving us the option to set the DC value of my voltage, because this expects that this is a DC voltage supply. However, I need to change it to an AC voltage supply. So I will click Advanced, and you can see that here we have many options what type of voltage supply this can be. So I will choose a sine wave because I want to simulate an AC voltage. I will select 0 voltage offset. I don't want any offset in there. Let's select, for example, 10 volts amplitude. For our simulation, it doesn't really matter what will be the amplitude. It will have an effect on the current, but not on the properties that we are exploring in the simulation. And since I want to simulate the situation in an AC power network that we have, I will select 50 Hz as my frequency. Now I can see that it already defined this properties of the voltage supply in my circuit. I can of course drag it somewhere so that it's not going over my description of my resistor. So I can drag it, for example, like this. And I need to define also my parameters of the inductor and of the resistor. So let's say for the time being that I will have a resistor of 100 ohm. You can again access the properties of the resistor by right clicking on the component. So I'll select 100 ohms. And since I want to start with the almost resistive load, I will set this inductance for a very small value. I cannot set it to 0, but I will choose some small value, let's say 1 picohenry, which is something very small. Even on typical printed circuit boards you will find something in the order of nanohenries. So here we are about 3 orders of magnitude smaller. So this will assure that we have a pure resistive load. The next step is to set the parameters for our simulation. So we can go to the menu Simulate, and we can edit our simulation command. Now the way LTSpice works is that it will insert a text simulation command into our circuit, as we will see in a second. And this simulation command then is telling the simulator that runs in background what should happen with the circuit. So if we select that, we can see what options do we have for our simulation. Now we will do a transient analysis. So we want to plot the voltages and currents in our circuit as a function of time. So that's the transient analysis. Now if we were interested only in let's say DC circuit for voltages and currents, we could do a DC analysis, or we could do DC sweep, and this basically is able to change the parameters of our circuit that we defined and then plot us the result. But for this class and also for the next one, we will be doing only transient analysis. Now I have used 50 Hz frequency in my circuit. So for this reason I want to see only few periods of my signal. 50 Hz frequency corresponds to the period of 20 milliseconds. So I want to see first few periods of my voltage signal. So let's say I will use the simulation time until 200 milliseconds. So this should give me 10 periods of my signal. I can also change the maximum step. Since I have the stop time 200 milliseconds, let's say my maximum step size will be 1 millisecond. We don't need that much fine calculation, so this will speed up the simulation, and this means that in the worst case scenario I should have about 20 points for one period. Now here we can see that what will be the simulation command that will be automatically inserted into our circuit. So it's a transient analysis from 0 to 200 milliseconds, and here are my parameters for the maximum step. So now I can just hit OK. I can place the simulation commands anywhere in my circuit, so I'll keep it like this on screen so that we may eventually change it, and I can run my simulation. So let's do it. We go to simulate and run, and now we will be able to see the result. I will just close my previous project so that we have only this one open. So now we can see that here we have our circuit, and on the bottom we will see our simulation results. Now I don't see any results right now, and the reason is that I did not select what I want to display on my circuit. So I will display the voltage that I have here on my circuit, so this voltage that's coming from the power supply. So this will be a sine wave, so you can see that now when I hover above my wire we can see this symbol of a probe. So I just left click on that and we can see that this will be my voltage shown here in green, and if I hover the mouse over my component I can see that the symbol is changing, and this is showing the current probe. So like this I can very simply click and I will see the current. Now I will just change the color here of the current to something else, because probably if I change it to red one it will be better with visibility, and we can explore now what we see on this chart. Now remember that this is an RL circuit, however the inductance is almost zero, very small, so it's nothing else than a pure resistive circuit. Here we have this resistor. It means that the current and voltage will have zero phase shift, and we can actually see it here. The green curve is my voltage and the red curve is my current. So even if I zoom in into my circuit, we'll see that the voltage and current is exactly in phase, so there is zero phase shift between my voltage and current. Now note that the voltage and current has a different scale. We can see here on the left we have the scale for voltage, and on the right we have the scale for current. And the fact that they have the same amplitude is only a coincidence of my selection for the scale of voltage and for the scale of current. If I change the value of my resistor, it will change me the scales, but here we still see zero phase shift between voltage and currents. You can see here also the sampling period of my calculation. We can display the measured points here actually. If I right click on my chart, and now I can select what I want to see, so mark data points for example, we can see those small dots are where it did calculate the result, and those lines it's only a connection, like in a linear way. So in fact our circuit was calculated only in those points. I can have a more accurate simulation if I decrease the sampling time of a calculation, but we don't need that here in our simulation. What we can do is that we can now play with this chart. We can also split this chart into two so that we can see the voltage and current in individual charts. So if you right click on the chart, we can see here we can add the plot pane, which is the second chart, and now we can see okay it's split in two, and I can simply drag my voltage on the top chart. So now here we have the voltage in our circuit, and this is the current. Let's take a look what will happen in our circuit if we change it from purely resistive into inductive circuit. So I will change the inductance here, and let's say I will use 10 millihenries for example, and I will decrease my resistance. So now it will have for example 1 ohm. So now I have an almost pure inductive load with some very small resistor connected in series. Now this resistance may represent for example the resistance of the wires in the coil. If I rerun the simulation, we will see what will happen with the currents and voltages. Now we can see here that the voltage, all is still a sine wave, but now when we have a peak of our voltage, it takes some time before we have the peak of my current. We can actually select a cursor here so that we can see exactly the time difference. So if I left click on my voltage here, you can see now I have this cursors, and I can drag it for example to the peak that I have here. In the window that we have in this part, we can see the amplitude and we can see the time shift, and here on the bottom we can again click on this chart, and I could now read my time here when I had 84.86 milliseconds, and I can drag it to my peak here, and I have some other time. So from the time difference I could calculate the phase shift. You know that one period corresponds to 360 degrees, and we can see here that it's an inductive load, because first we have the peak of the voltage, so voltage first, that's here, and then we have the peak of the current, and here we can see now I have enabled both cursors on voltage and on current, so we can see that the time difference is this one, and if we know that the period is 20 milliseconds, we can calculate what will be the phase shift. So now in our circuit we have an inductive load with a resistor. If this would be an ideal inductive load, so zero resistance here, we know from the theory that the phase shift between voltage and current should be 90 degrees. So let's see if it will be true also in our simulation. Let's change this from 1 ohm to, let's say, 1 micro ohm for example, so that now we will have a very small resistance and a fairly large inductor. And in the simulation we should see that now the phase shift has changed. So now when I have a maximum here of my current, the peak of my current, here I have 0 voltage. So this is an ideal inductive load with a phase shift of 90 degrees between voltage and current. Now let's take a look on how we can use the simulation results to plot the power that we have actually in the circuit. We know that instantaneous power is calculated by multiplying the voltage with the current in the circuit. So if we have this kind of circuit, I will multiply the voltage that I have here on this node. This is the voltage from the power supply, V1, with the current that is flowing in my circuit. So this is either the current in the inductor or the current in the resistor. They're both the same because they are connected in series. Now for our first experiment, I have set back the circuit parameters to 100 ohms here. So this will be resistive load, and to a very small value of my inductance. So we'll start with a purely resistive load. And the second change that I've done is that I have decreased the simulation time to just 100 milliseconds, because I want to see only the first 5 periods of my signal. Let's run the simulation, and here we go. So we're back at what we've seen originally. We have a sine wave of voltage and a sine wave of current, and there is zero phase shift between the voltage and current. Now, one of the reasons why we are doing this in LT-Spice and not in PartSim like last semester is that in LT-Spice we can do some calculations with our signal. So if I now right click anywhere on my chart, I can add some traces, and I could add other voltages, other currents that I have in my circuit, but I can add also some expressions. So I want to calculate the instantaneous power, and I know it's voltage times current. So here that's the name of my voltage, VN001. So that's my voltage in my circuit, times the current in my circuit, which is IL1, and this will give me instantaneous power. So now if I just hit OK, we can see the calculation results. We have a new trace here, which is voltage times current, and we have a new scale on the right, and the simulator knows that if I multiply voltage by current, it will give me watts. And we can see that for the resistive load, the power that we deliver into the circuit is always positive. You can see it starts from 0 and it peaks here, and exactly the same peak as we have the peaks of our voltages and of our currents. Here we're simply multiplying positive number by positive number, so we have some positive result, and here we multiply negative voltage with negative current, so we have a positive power. So we can see that for a resistive load, the power is being transferred only from the power supply to my resistor, and there is nothing going back, and it's always positive. Now if you would like to calculate the average power, then you are basically calculating the area under this waveform. So if you should calculate the integral let's say from 0 time until 1 period, and this would give you the average power. Now let's see what will happen with our power if we have an inductive load. So I have changed the inductance to 10 millihenries and the resistance to 1 ohm, and I will run the simulation with the same parameters until 100 milliseconds. Now we can see that something happened with our power. We have a sine wave of voltage. We know that the current is shifted by some phase shift, and this means that if I have a peak of voltage, I don't have the peak of current, and basically there are areas where I'm multiplying positive voltage with negative current, and also areas where I have negative voltage and I multiply that by positive current. So it's clear that in the power we will have areas where the power will be positive and where the power will be negative. And this is exactly what we see here on our result. So here we have about 20 watts of power, but here we have about minus 10 watts. So it means that the power is being delivered from my circuit back to the power supply. So it's traveling back and forth between the power supply and the load. So on the class you will do this analysis in more detail with different kinds of circuits with different values of the parameters, and you will plot various types of power that we have here in the circuit. At the end, let me note one interesting thing that we can see here in the circuit, and that's here around the beginning of our simulation. Now we did not see initially any deformation of our signal if it was a resistive load. However, now we have an inductive load, and for this reason we can see a transient when we turn this circuit on. So you can see that the voltage, the green sine wave here, starts from 0, and the current starts from 0 as well. But you can see that the amplitude of my current now is changing. It's initially larger than we have at the end, and this is because here now we have turned this circuit on, and this is where the transient is happening. So in AC circuits we also need to wait for a steady state. However, the steady state here does not mean that we have a constant voltage or current in the circuit in terms of like a DC value, but we have a constant magnitude and constant frequency in our circuit. So here you can see that we have a larger current and then it's decreasing. Of course, it's possible to calculate by analyzing the circuit and by writing the differential equations how the current will be changing. In our simulations that we will do, we will always assume that we are in steady state, in AC steady state. So we are somewhere around here where we have a magnitude and frequency of the current that is not changing. You can see that it has also a large effect here on the power. So initially we are taking larger power from the power supply when we turn it on, and then the magnitude of my power is changing, and then we are somewhere at steady state here where we are taking and delivering constant power to and from the power network. Now at the end, let me show you a bonus, and that's how we can calculate the average power directly in LTSpice. We can of course take this data and we could integrate them manually and we could calculate the area. However, there is already a function in LTSpice that can calculate the integral for us. So I want to calculate the integral of the power that I have here on my blue curve. It's very easy. You just hover above this power that you have calculated. You press Control on your keyboard and then left click with your mouse, and we can see that this will be my integral. So it starts from 0, it's going to 100 milliseconds, and this is the average value. So if you take the wattmeter, for example, in the circuit, you should see this power. However, there is a catch. Now the problem in this calculation is that here this includes the integral of my transient here on the beginning. So we can see that here we have a larger power, and then the power has changed somehow, and then it's going to the steady state. So if I want to really see my steady state value of the power, I need to zoom to a different area of my chart so that I exclude from the integration this beginning of my circuit, of my current. So for example, I can zoom in like that, and now I have a fairly good sine wave. And if I do it again, here I just hold Control on my keyboard and left click on my current, and we can see that I have about 5 watts of power. Now the power has decreased because now we have removed the larger peak that we had on the beginning. It doesn't matter how large my interval is, because the average power is calculated over this interval, so it basically does not matter if I calculate the integral from one period or from several ones. Of course, this is valid only if I have enough sampling points in my calculation like that. So in this way you can very easily display what is the power in your circuit. And now if you calculate, if you want to calculate different kinds of powers, you just need to insert the correct formula in the waveform and then display the integral like that.